Hey guys, today we're going to talk about the world's largest aquifer, the Ogallala Aquifer. It's really fun to say. The Ogallala is found under 8 of our states in the United States, and it is absolutely huge. There's enough water in this aquifer that could cover the entire United States with a half a meter of water. As you can see, it extends all the way from South Dakota to the Texas Panhandle, but it's not really consistent throughout the aquifer. There are high concentrations and depths and volumes in the north, especially in Nebraska and South Dakota, and it sort of dwindles as we move to the arid south. This is a function of today's climate as well as prehistoric conditions, because this is considered a one-time deposit. Many consider it a fossil aquifer that has incredibly slow recharge rates. It was created after our last ice age, when the Wisconsin glaciation retreated back north. And of course, in its wake, all of that fresh water that melted accumulated and was stored in porous limestone rock and porous sediment material throughout the high plains. Of course, it is this site, the high plains, that serves as our breadbasket and helps sustain the American economy and keeps us fed. The high plains cover 6% of the United States, and they are our breadbasket. They produce more than 15% of its wheat, corn, and cotton, as well as 40% of our livestock. The problem is wheat, corn, and cotton, they are really, really thirsty crops that are not suitable for the high plains climate. It's too arid and too dry, and so it's not really sustainable. So in order to grow these crops there, farmers have had to rely on the Ogallala. In fact, 30% of the irrigation water that's used in the United States is coming from the Ogallala to support these crops that are not really suitable for this location. What this means is that we are withdrawing groundwater at a rate that is not going to sustain the Ogallala in the future. The rate of recharge is way too slow. It doesn't recharge fast enough on a human time frame. And therefore, it is declining and depleting 10 to 40 times faster than its natural rate of recharge. In some areas, water tables have lowered more than 30 meters. By the end of this century, and perhaps by the middle of it, there might not be enough water to economically pump it and to utilize it for our agriculture. These are scary predictions. Part of the reason for perhaps our inefficient use of the groundwater and our inability to conserve this water resource is the fact that the price of water and irrigation water doesn't have a true value. In other words, it's artificially low. Farming subsidies have kept the prices of this groundwater at a very, very cheap price. And when you have a cheap price for something, there's very little incentive to conserve it and prevent its waste. Furthermore, technologies that would conserve it are perhaps cost prohibitive to many farmers. They're very expensive, and currently they don't have the proper tax advantages or subsidies to make them more competitive to encourage conservation. Instead, we've relied on age-old techniques that are very inefficient, very cheap. Furrow irrigation, for example, involves cutting furrows between crop rows and filling them with water. This actually promotes runoff and evaporation, making it very inefficient. But it's cheap. Unfortunately, 1/3 of the water is lost to evaporation and runoff. Similarly, flood irrigation, where water simply spills out over the crops. More runoff, more evaporation. Much water is wasted through these processes. There are techniques and strategies that do conserve water, and efficiency is improved when various sprinkler technologies are incorporated, delivering water in a more precise way. Sprinkler technologies have improved dramatically. Some sprinkler heads deliver water far more precise than old technologies, and various strategies like center pivot have improved the efficiency up to 80 to 90%. Center pivot uses concentric circles of crops, and then it actually uses a large boom with a series of sprinkle heads on it. And that boom, as the radius of the circle, circumnavigates that crop circle, delivering water in a very precise manner. By far the most efficient form of irrigation is drip irrigation. It's still cost prohibitive in many parts of the world. However, the efficiency can go up to 95%. And what it uses is a series of perforated tubes that can be manipulated to follow the root system of the crops. Being buried prevents evaporation, and that tube just slowly releases water in a sort of a trickle so that there isn't excessive amounts of water used, soils don't become waterlogged, and little evaporation and runoff occurs. Aside from overusing groundwater, there's other consequences to irrigation. In arid locations, repeated irrigation can result in the process of salinization. Irrigation water contains small concentrations of dissolved salts. So if you irrigate your field, the water will eventually evaporate, but the salt doesn't go anywhere. One dose isn't going to hurt. However, repeated irrigations and repeated applications of irrigation water will start to accumulate salts in the soil. This can prove lethal and reduce the productivity for our soils. One solution to salinization, however, is to continue to flush the soil with more water. The idea here is to leach those salts further into the soil away from the roots. This can create its own set of problems, however. By supersaturating the soil with excessive amounts of irrigation and more water, the water table actually rises to the point where the soil has become saturated, anaerobic, and without oxygen, the plants will die. That's it for today, guys. We'll see you soon.